In this video, we're gonna learn on how to solve first-order differential equation by the means of solutions by substitutions. Now, the main idea of solutions by substitutions is to solve a non-familiar differential equation by converting it into one familiar differential equation by means of substitution. Since we've already tackled the variable separable in our differential equation. Now, say we have a first-order differential equation in this form, m dx plus n dy is equal to 0, where your m and n are both functions of x and y. Say this equation is said to be homogeneous if both m and n are homogeneous. Now, both of m and n are homogeneous if and only if these equations below are satisfied. Now, these equations say if you plug in tx and ty to m and n instead of x and y, the resulting function should be in this form, t to the alpha times m of x and y, or t to the alpha times n of x and y, where we could still factor out the any power function t to the alpha and could still express the other factor to m of x and y or n of x and y. Now, if the differential equation is homogeneous, then we can use these substitutions below here. Y is equal to ux or x is equal to vy, where your u and your v are the new dependent variables, and will reduce the differential equation into a separable first order differential equation. Now, to understand further, we should we should solve an example here. We are given this differential equation here, y dx is equal to 2 quantity x plus y dy, and we should express this in terms of m dx in the form of m dx plus n dy. We have y dx subtracting 2 times x plus y dy to both sides of the equation. That's why we have negative here, 2x there, transfer that here, and changing the sign we have this. Now our m of x and y is this. Our m is simply y, the coefficient of dx, and our n is what? Negative 2 times x plus y. Now plugging in tx and ty here instead of x and y, since this is m in terms of y, then we should change all the y with ty and all the x with tx. Since this is just y, we should change this to ty. Now, since our m of tx ty is just ty, this here, this is after changing y with ty. We have ty here, and since our y is just our m of x and y, then we already expressed there this m of tx ty into this form, t to the alpha, where your alpha is 1, times your m of x and y. Since your m is just this, the y here, and your n of tx ty, replacing all the x with tx and replacing all the y with ty, To solve for our ntxty, we have negative 2 times dx plus dy, and factoring out the t, we have our ntxty as factoring out the t, we have t, and we're left with negative 2 times x plus y, where your negative 2 times x plus y is just your n. So meaning we have already expressed our ntxty in terms of some t to the alpha times n of x and y. So meaning both m and n are homogeneous. Now after knowing that our equation is homogeneous, since we've already known that m and n are both homogeneous, then we'll try to solve this problem here. We'll try to rearrange this in this form here. Dx over dy we will now try to solve our differential equation after knowing that these m and n are homogeneous. And dividing dy to both sides of the equation, we have dx over dy, and dividing again by y, then we have 2 times x plus y over all over dy, all over y I mean. So we have our dx over dy as 2 times x over y plus y over y is 1. So meaning if after knowing that our differential equation is homogeneous, we should choose from these: y is equal to ux or x is equal to vy. So since we're more comfortable with choosing this because our expression is now in terms of x over y, since we have a pattern here, we already saw that our equation has this pattern x over y, so we'll use this. We'll let v is equal to x over y, or x is equal to vy. We let v is equal to x over y. Now let's try to solve that in the next page. Letting v is equal to x over y. So our x now is v times y. And taking the differentiation with respect to y, we have dx, the derivative of the left hand side expression with respect to y, is equal to the derivative of right hand side expression by product rule. We have v dy over dy over dy plus y dv over dy. So from our original differential equation, we have dx over dy is equal to 2 times x over y plus 1. Now let's just plug this in here in our left hand side expression. V, since we can neglect this, since dy over dy is just 1, so we can cancel this. So our dx over dy is now v plus y dv over dy is equal to 2 times our x over y is v, so we'll change this to v plus 1. Now subtracting v to both sides of the equation, 2v plus 2 minus v, 2v plus 2 minus v is just 2v minus v is v plus 2. So this cancels out. We're left with y dv over dy is equal to v plus 2. Now multiplying by dy over y dy over y times v plus 2. Our left hand side now is cancel, dy over dy cancel out, y over y cancel out, so we have dv over v plus 2 is equal to our right hand side, we can cancel this v plus 2 here, v plus 2, so we're left with dy over y. So taking the integral of both sides of the equation, so that we'll have our solution now. Integral of dv over v plus 2 is just ln of the natural logarithm of v plus 2. And the integral of dy over y is just the natural logarithm of y. Plus a constant. You can put the constant to either sides of the equation, but I like to transfer ln of y here is equal to ln of v plus 2, but your v is just x over y, this. So let's plug that in here so that our solution is in terms only in x and y. X over y plus 2 plus c. Now you can check this answer is correct here. This is our solution, and ln of y is equal to ln of x over y plus 2 plus c. This here is our answer.